On Wednesday, we're going to be talking about using partial fraction decomposition to help us integrate some pretty complex rational expressions where U substitution is not going to help us, and we might not necessarily see sums and differences of squares right off the bat. So I want to just give you a little introduction and give you a head start. That way we can make sure that we finish this section on Wednesday and we're ready to test next week. I'm not certainly going to cover this in this whole concept in the video. Again, it's just a quick little introduction. I'm going to try to keep the video pretty short. And I'm going to have a couple of questions embedded along the way for you to answer. So I'm going to get going. So first I'm going to show you what this looks like backwards, because it's actually something that you've done before. So back in like a beginning algebra class, I might have asked you to, or somebody would have asked you to add maybe 3x over x minus 2 plus 5 over x plus 1. They would have asked you to add those two fractions together. So if we wanted to do that, we would have to get common denominators. These two denominators do not match. And whether those denominators are numbers or whether they have variables, in order to add or subtract fractions, we have to have common denominators. So we have to get common denominators in order to add these two fractions together. So I'm going to multiply top and bottom by x plus 1 over here, and top and bottom by x minus 2 over here, so that we can get a common denominator of x plus 1 times x minus 2. When I get my common denominator, I can then add my numerators. So I'm going to rewrite what I'll have. Here I'm going to have to distribute. So I get 3x squared plus 3x over, and I am going to FOIL these and see what that new denominator is. It's x squared minus 2x plus 1x is going to be a minus x, and then minus 2. And then we need to distribute here. That's going to be 5x minus 10 over. And then if we FOIL here, we should get the same denominator because it's got the same two factors. It's x squared minus 2x and plus 1x is a minus x, and then a minus 2. And yet we do have the same exact denominator, which means we can add those fractions together by adding their numerators. So if we combine our numerators, we can combine like terms and get 3x squared plus 8x minus 10 all over our common denominator of x squared minus x minus 2. So that's what we would say the sum of those two fractions are. So this is like an intermediate algebra problem. We would have two fractions with variables in the denominator. They do not have common denominators, so we would have to get common denominators and add them together. When we do partial fraction decomposition, we're going to reverse this process. We're going to start with some complex, pretty complex rational expression that looks like this, and our goal is going to actually to separate it into much simpler fractions that look like the originals that we started with. Because here in chapter 7, we're trying to integrate. So if I wanted to integrate 3x squared plus 8x minus 10 over x squared minus x minus 2, if I could get that separated into two separate terms, we can integrate them individually. And this started out as 3x over x minus 2 plus 5 over x plus 1. Now, if we can get them separated with addition or subtraction, then we can integrate them separately. Now here, it's all in one big piece. So we've got to figure out a way to integrate it all as one big piece. Right now, all we know is U substitution, or if it's a sum or difference of squares, we can do trig substitution. And neither one of those is going to work here. We don't have a sum or difference of squares, and U substitution is not going to work. So if we could figure out how to turn this into this, which is really just undoing the addition problem, we can then integrate. So we are undoing this find common denominators and add. We're separating back apart. So that's where this decomposition word comes from. We're pulling them back apart into individual pieces. It's decomposing. And partial fractions means we're taking one giant fraction and plucking it out into little pieces, into little partial pieces. So how exactly do we do this? It all starts with factoring. If you look at the denominator we start with and the denominators we end up with, these two guys are just factors of the original. So it's always going to start with factoring. And we're going to be able to create denominators for each of the factors. Once we create a fraction that has a denominator with each factor, we're then just going to do some algebra to figure out which numerator is going to make the numerators match. And there is a rule about how we set up those new fractions and how the denominators work. So I'm going to go through the rule on how we set up these fractions, and I'm not going to do a whole lot more than that, and we'll talk more about it on Wednesday. So there is something called the fundamental theorem of algebra. I feel like I'm spelling that wrong. It's all right. And the fundamental theorem of algebra says that every polynomial, every real valued polynomial, and not even real valued, let me say polynomial with integer coefficients, can be factored into linear and irreducible quadratic factors. All polynomials that have integer coefficients can be broken down and factored into linear and irreducible quadratic factors. So every single denominator that we work with is going to be factored either into linear pieces or these irreducible quadratic pieces. So we may have quadratics that can't factor further. So how we set up these fractions for the linears and the irreducible quadratics are just a tiny bit different, but there is a pattern that they both follow. For each unique linear factor of the form, and this is going to look really weird, this kind of general math notation, but then I'm going to show you an example. Ax plus b to the m. So that m means that it's a repeated factor. So I've got one linear factor that shows up several times in my factorization. So for each unique linear factor of the form ax plus b to the m power, we're going to include the following fractions in the partial fraction decomposition. we need to make sure that all of these fractions are proper fractions. So since these denominators are going to be linear, a proper fraction will always have a numerator that is 1 degree or less smaller. So since these are linear, the only smaller degree than that that's still a polynomial would be a constant. So we start off with just one of them. So a over ax plus b, and then we're going to work our way up in powers until the number of times that that factor got repeated is how many times it got included in our decomposition. Now, this is not going to happen a lot. You're not going to have 20 of these. At the absolute most, in a really tricky problem, you might have 3. Usually you'll only have 1. In a rare instance, you might have 2. Again, in a really challenging problem, you might have 3. But most of the problems, you'll just have 1 of them. So for each linear factor, the factor goes in the bottom, and then a constant goes in the top. And every single fraction is going to have a different constant numerator. For our irreducible quadratic factors, so I'm going to say the same thing. For each irreducible quadratic factor, of the form ax squared plus bx plus c to the n, because it might get repeated multiple times, which is very rare, but it's possible. In case it ever happens, we need to know what to do with it. So for each irreducible quadratic factor of the form ax squared plus bx plus c to the n, include the following fractions in your partial fraction decomposition. And now these are going to look a little bit different, but they're going to follow the same pattern. So with the linears, we wanted our numerators to be a power smaller. And we needed as many fractions as the number of times they got repeated. So those two things are going to be the same. Since these factors are quadratic, our numerators are going to be a power smaller. So we're going to start with one of them. Since it's a quadratic, 1 power smaller than that will be a linear equation. And if this gets repeated n times, I need to work my way up to n of them. So next I'm going to have 2 of them. I'll say this is cx plus d, because all of those numbers could be different. And I need to work my way up to n of them. Now, it's going to be very rare that we'll have a repeated quadratic factor, but just in case we do ever see it, we need to know what to do with it. Now, I have no idea what these would be, but I just need to make sure that they're different. So our quadratic factors are going to have linear numerators. And however many times that quadratic factor is repeated in our factorization, we start with just one of them and we work our way up. Now let me show you an example, because this description can be kind of confusing when we're using all of these letters. Let me just show you an example. We're going to write out just the basic partial fraction decomposition. We're not going to solve for any of those unknown numerators. We're just going to write out what the basic setup would be. 2x minus 5 over x squared plus 9x plus 20. Our goal is to break that apart into simpler fractions that are either added or subtracted. Now, we're not going to know if they're added or subtracted until we know what the numerators are. We're just going to assume that they're added right now. The first step is always to factor your denominator. The factors of your denominator are going to tell you what your new, smaller denominators are going to be. So we have to be able to factor this guy. It's a quadratic, so it's most likely going to factor into two linears. We're looking for two numbers that multiply to be 20 and add to be 9. That's going to be x plus 4, x plus 5. And I only have one of each of them. So that means when I set up my partial fraction decomposition, I only need one fraction for each of them. However many times they're repeated, that's how many fractions you need for them. They're each only there once, so I only need one fraction for them. So they each get to go in their own denominator separately, and because they're linear, the powers are going to be one smaller, so my numerators are going to be one power smaller. My numerators are going to be constants. This is the basic setup of our partial fraction decomposition. After that, we've got to do some algebra to solve for the a and the b. If we can figure out the a value and the b value, integrating is going to be a piece of cake, because we now just have these two separate fractions with linear denominators to integrate. And we'll talk about the integration later after we get the partial fraction decomposition down. So for the next one, we are going to do x to the 4th minus, let's say, 15x squared minus 16. We've got x squared plus 9 divided by x to the 4th minus 15x squared minus 16. We just want to set up the basic partial fraction decomposition. We want to know how I can break that up into several different separate fractions. Another way you can think of this is somebody was asked to add multiple fractions together, and they did it correctly. But what we want to do now is separate them all back apart. So this is the final answer to an addition problem, and we want to know what the original question was. So it always starts with factoring. We need to start by factoring this guy. This is quadratic in form. It's a trinomial. We should be able to factor it into two binomials with x squareds in the front. We're looking for two numbers that multiply to be negative 16 and add to be negative 15. And that's going to be a minus 16 and a plus 1. Now be really careful because we can factor further. X squared plus 1 is an irreducible quadratic, but x squared minus 16, that's a difference of squares. That will factor to x plus 4, x minus 4. So I've got two linears and a quadratic. There are three different factors. Two linears and a quadratic, which is three different factors. I'm going to have three different fractions. None of them are repeated. None of them have a power on the outside. So I get to separate them all into their own individual fractions. The linear factors get constant numerators. Quadratic factors get linear numerators. And you need to make sure they all have different arbitrary constants. There's no guarantee that any of them are the same. Once we get the basic set up, after that, the next phase we go into is trying to figure out what those arbitrary A, B, C, D constants are. And I'm going to show you one more. So this is our basic setup for our partial fraction decomposition. This would be easy to integrate. This would be easy to integrate. That one is a sum of squares. We could potentially integrate that one with trig substitution. We could also separate this into two pieces and do one with u substitution. And usually a sum of squares with no square root around it, I think we actually have a formula for that. It might be an arctan. I can't remember off the top of my head. I think it is. I think that's arctan. But the basic idea is once we get these separated with pluses in between, now they're three separate terms and they can be integrated separately. When they're all together in one fraction, they can't be integrated individually. All right, last one, and this one's going to have a little twist to it. We've got 5x minus 3 over x cubed minus 2x squared. We always start off with factoring our denominator. The factoring here is going to involve pulling out a GCF, which is x squared. If we pull that out, we're left with x minus 2. Now, I need to tell you something about this x squared in the front. This is not a quadratic factor. This is a repeated linear factor because you could technically write that as x times x times x minus 2. This is a single factor that is there twice. That is a linear factor that is in that problem twice. That is a repeated linear factor. Which means when we set up our partial fraction decomposition, I'm going to need two fractions for that. The repeated factors are often the trickiest to remember. So it is a linear factor. So what kind of numerator is it going to get? Linear factors get constant numerators. You start with just one of them, and you work your way up in power until the power matches how many are in the factorization. So I start with 1 and then I work my way up. There's only 2 in the factorization, so I can stop at 2. And then my other factor is x minus 2. That is also linear, so it gets a constant numerator. So linear, not necessarily linear, but repeated factorizations or repeated factors are going to have multiple fractions representing them. You start with just one of them and you work your way up until the power matches what you have in the factorization. Now that squared does not mean quadratic, it means repeating. If the squared was on the inside of the parentheses, that would mean quadratic. You can think of that as the square being outside the parentheses, which means repeating. So this would be our setup. All three of those are easily integrable. Turns into a log, a power rule, and a log. So you can see how all of these, once we get them separated, are much easier to integrate. So this is a very, very useful technique for integration. Most of the work is algebra work, though. Probably 80% of the work that we're going to do with the partial fraction decomposition is algebra work. And then once we figure out the basic setup for the partial fraction decomposition, we've got to solve for those numerators. Once we solve for those arbitrary constant numerators of the capital A, B, C, then we're ready to integrate. And almost always these antiderivatives turn into logs or power rules or inverse tangents. Almost all of them. So this is just a little preview of what we're going to be talking about on Wednesday. This will take most of the day on Wednesday, and we'll just do a lot of practice with these and see some more examples with the factoring and the setup, the basic setups, and we'll talk about how we're going to solve for those A's, B's, and C's and go through some full problems from start to finish with the integration and all of that stuff.